Thank you for joining us today. Um, we wanted to go over how does vSAN work with Intel Optane SSDs in data analytics. Kind of give you an overview of how does the new hardware technologies enable vSAN to provide better performance in data analytic workload, right? So let me go over a few basic things on how does vSAN work, what does Intel Optane SSD do, and then jump into the Spark scenario and see the performance that comes out, right? So if you look at the vSAN architecture, right, it's basically a 4-node vSAN cluster that we tested. What the vSAN architecture does, or the vSAN as a whole does, is it takes a group of servers,
Stay away from the speaker.
takes the storage devices that are there in the servers, and virtualizes that storage and makes it into a data store. And the data store is being given to a bunch of VMs that are present. Okay. Now, if you look at how each of the node itself on its own, how does it function, and how does the read-write operation take place inside a vSAN architecture? What you see is you have two tiers of storage. One is your caching tier, and the other one is your capacity tier, right? So if you look at the I/O path that's going in, what you see is the caching tier acts as a 100% write buffer. Okay, so all the writes go to the caching, and once the writes are returned to the cache, then it sends back an acknowledgement telling that it's completed the write and puts it back to the VM, right? So now, after a period of time, once the buffer starts filling up, it destages the data to your capacity tier. Okay. So once the destage is complete, all the reads that come out from the capacity tier. Okay. So let me repeat this again. The caching tier acts as a 100% write buffer. All the writes go into it. After destage, your capacity tier acts as a read, right? So all the reads come out of the capacity tier that's there. If there's a hot read scenario that comes out, right? When I say hot read, what I mean is, as soon as you write, there's a read operation that comes out. That gets serviced by the caching tier. Okay? So take this scenario and look at how does Optane SSDs help, right? If you look at the Optane SSDs, there are a few key characteristics that help in a 100% write buffer scenario like a vSAN, right? The first is latency. So I wanted to show you some numbers on how does the latency work, how does the endurance work for an Optane SSD, and how does this benefit from an overall architecture perspective, right? If you look at the graph that you have on the left, it's basically a write pressure test where you have a bunch of 4K random writes that are being done, and you see what's the read latency that's coming out from comparing it with a standard NVMe device to an Optane SSD. Okay, so what you see is over a period of time, the latency goes across on a standard NVMe, right? And what you see in the blue line that's there is Optane's latency pretty much stays flat. Okay, so just comparing it over time, the standard SSDs kind of rise from a latency perspective compared to an Optane SSD where the latency remains flat over a long period of time. Okay, now most of the workloads usually are falls in the range of the 8 to 10x difference from a latency perspective, right? And the 63x is more about how can I push my SSD to a long amount of random write operations and see what comes out, right? So that becomes your worst case scenario that you're looking at. Okay, so that's one. The key thing there is the latency scenario. The second aspect is the endurance. If you compare the standard NVMe SSDs that are there in the market today, you're looking at around 3 drive writes per day for some of the newer ones that have come out, right? Compare that with an Optane SSD. With an Optane SSD, you're looking at around 60 drive writes per day. It goes up to 60 drive writes per day. And in a scenario where you're looking at 100% write buffer, the amount of write operations that's happening is huge. And endurance plays a big factor in how the device fits in that particular use case, right? So it becomes a perfect fit for a vSAN architecture where you have a 100% write buffer scenario, and Optane with its endurance and low latency and the higher IOPS falls right into it, okay? So this kind of translates to, hey, I don't need a large amount of caching device. I can end up using a small amount of Optane and replace the large amount of caching that I currently have, right? So VMware came out with a blog explaining this whole concept of how does it work, how does the whole endurance scenario affect the size of my caching, right? There's a detailed table that's been put out on this blog that gives you, okay, how does different I/O patterns affect how much of standard SSDs do I need and how much of Optane SSDs do I need, right? So there's been quite a number of tests by a whole lot of bloggers and press around the world on this, and this one of the nice quotes that I like is, use Optane as your default caching tier device when you're using vSAN, and that's a pretty good statement, right? So I wanted to give an introduction on how does Optane fit in a vSAN architecture, and kind of go over from there, right? And Ahmed, who's been doing the testing on the Spark benchmarking, will go over in detail on what kind of scenarios did he see and the numbers that's come out.
Okay, thanks, Vivek. So this is Mohamed Elsaid. I'm a cloud specialist at Intel. So the objective of this test bed is to show what is the performance gain of having Optane inside vSAN in data analytics environments. Okay, so from time to time we see customers who are interested in building new cost-effective, high-performance data analytics solutions, and we see that Optane is fitting well as a cache layer for the vSAN environment. So for this objective, we have built a test bed with this environment. So we have Intel Optane as a cache layer for the vSAN data store, and we have 4 nodes clusters, and we have built a shared distributed file system, which is GlusterFS. So as you know, HDFS is the normal distributed file system for data analytics. However, we see Gluster file system has comparable performance. However, it is much easier and much straightforward in deployments. So we have used the Gluster file system as a distributed file system for the data analytics environments. And on top of Gluster file system, we have deployed Spark cluster in a standalone mode with 8 workers and 1 master node. So this is the data analytics environments that we have built. I will go in deep with each layer details and configurations. And for the benchmarking, we have used TerraSort and TerraGenerate as a benchmarking tool for Hadoop clusters and data analytics environments. So basically, for the servers specs, we have used Pearl Skylake servers in our Intel labs with dual sockets per server. Each socket has 20 physical cores, and the server has 384 gigabyte of RAM. And for each server, we have just 2 Intel Optane drives that act as a cache layer for the vSAN. And for the capacity tier, we have 4 NVMe drives. These are Intel NVMe SSDs, which is a P4510 in 2 terabyte capacity per disk. And for the network backbone, we have used the 10 gigabit Ethernet Intel cards. And each server is ESXi 6.7 version, which is the up-to-date release by VMware. Yeah, for the vSAN environment, we have created one vSAN data store from these 4 servers, and it's a vSAN 6.7 in all flash configuration. And the system memory is actually the aggregate memory and the aggregate cache and storage capacity of these 4 servers. We have TFF0 for the fault tolerance, and we have disabled the checksum because actually the checksum is already done by Gluster file system. So there is no need to have dual checksum also by the vSAN data store. Yeah, for the Gluster file system implementation, we have used the Red Hat Gluster file system 3.10.12. It's actually a set of virtual machines, and each virtual machine is a CentOS 7 release. Each virtual machine has 16 virtual cores and 128 gigabyte per VM. For the storage, we have 2 storage disks. One is for internal usage. This is for the operating system. And the other disk is actually the disk that will be used for the distributed file system. Okay, so the 4 terabyte disk is the disk that is used by each virtual machine for the distributed file system. And the 2 terabyte disk is the internal disk for the operating system usage. And there are different types of Gluster file system volume configuration. We have used the striped volume, which has concurrent parallel read and write operation to have maximum IOPS. There are different configurations like replicated configurations and replicated stripped configurations, but due to the low amount of servers that we have just 4 nodes, so we have used just the stripped volumes without replication. For that running test, we have used 2 tests to compare. We have 3 virtual machines of Gluster, so 3 nodes of Gluster, and the other test with 4 nodes of Gluster. One VM is 4 terabytes, so with the 3 nodes, we have 12 terabytes as a distributed volume. With 4 nodes, we have 16 terabytes as a distributed volume. And if you know Gluster, Gluster has their own native client protocol for the client access to the Gluster file system, which is called native client fuse for Gluster nodes. So we have distributed this fuse client on all Spark virtual machines in order to have the native protocol with Gluster file system that ensures high performance. Yeah, and finally, we have deployed the Spark cluster in a standalone mode. So we have used the Spark version 2.3.1. As I mentioned, in a standalone cluster, we have 1 master node and 8 worker nodes. And each worker node, as well as the master node, are all CentOS virtual machines. These are the specs of the virtual machines. They have almost the same specs like the Gluster file system. However, for the storage part, we have only 1 internal disk for the operating system, and the mounted file system from the Gluster is the one used for the loading the data and doing the read and write operations. Yeah, as I mentioned, for the benchmarking, we have used TeraGen, TeraSort, and these are the amount of files that are generated. So we have generated 250 gigabyte files for TeraGen and TeraSort. The same for half terabyte, 1 terabyte, 3 terabyte, and 10 terabyte storage. So this is, in brief, the test bed that we have used. This is actually the vCenter server view for the existing cluster. So as you can see, we have 4 physical machines. We have 4 Gluster file system nodes. We have 9 Spark nodes. The first one is the worker node. The first one is the master node, and the other 8 nodes are the worker nodes. Yeah, this is actually another view from Spark master node CLI. I mean from this view to show that this is Gluster file system. So as you can see, the TeraSort and TeraGen are operated on the Gluster file system share, which is in 12 terabyte for the 3 nodes and 16 terabyte for the 4 nodes. Okay. Yeah, for the benchmarking results, so as a brief intro for TeraGen, TeraGen is a random generated database benchmark. So it generates random data in a certain size that you specify. So for example, we specified 250 gigabytes, so it generates random data in 200 gigabytes. And then TeraSort is sorting this data that is generated. So for every test that we generate different size of data, and then we sort it. So this is a very well-known benchmark for Hadoop clusters and big data analytics environments. So for different sizes, these are the amount of delays that are consumed to generate the data and to sort the data in minutes. As you can see, for 4 cluster file system nodes, it is less than the 3 with almost 0.75 ratio, which is the ratio of the number of nodes. And in order to know how good these results are, we have compared these results with other white papers by VMware and by CNIA organization to see what is the performance comparison. So this is the white paper that is published last year, actually, in VMworld by VMware. It's about benchmarking data analytics with TeraSort and TeraGenerate. However, it's a different environment. It's an environment with 13 physical machines, HPE machines, with dual socket processor, Broadwell per machine. It has half terabyte of RAM, and for each physical machine there are 2 mechanical disks for 800 gigabyte NVMe and the 12 SAS drives for the capacity tier SSD. In this environment, they have used Cloudera, not Spark, and they have used HDFS as a distributed file system. So this is a very well-known environment for many customers to have Cloudera with HDFS. So as you can see, we compare the 4-node cluster file system with the white paper that is published last year by VMware. So as you can see, for the 13 physical machines, there is almost a factor of 0.4. Okay, so the consumed time in TeraGen and TeraSort is almost a factor of 0.4. So this means that for a factor of 0.4, we have consumed 13 physical machines. However, with 4 physical machines, we have consumed 0.4 of this value. This means, in other words, that if you have 10 servers of Perley, Skylake, and Optane, you can achieve the same performance of the 13 servers of the Broadwell-based CPU without Optane, okay, with simple calculation. So it means that with using Intel Perley, Skylake, and Optane, you can save almost 25% of the required number of servers. Okay, so it's actually very important for the TCO calculation, because some customers claim that Intel Optane is a little bit expensive as an SSD. However, it actually saves a lot of other servers needs from IOPS and latency requirements. Yeah, another comparison. Here it comes another white paper. It's actually a CNIA white paper in cooperation with Intel. So in this paper, there was a 1 per metal server, which is Perley, Skylake, and Optane. However, Optane in this environment is used as extended memory with IMDT, which is an Intel extended memory technology. Because it's a per metal, there is no virtualization, there is no VMware, there is no vSAN. So in this case, Intel Optane is used as an extended memory, not as SSD disk for a cache layer, because there is no vSAN layer, so there is no cache layer here. Okay, so it is used as an extended memory. And for the file system, Hortonworks is used. And for the capacity tier, there are 6 Intel SSDs. Okay, so as you can see, if we compare also the 4 nodes cluster from Spark with vSAN environment, with this per metal, it's almost a factor of 4, which means that the virtual environment has actually a very close results with the per metal environments. Okay, so it means that with Intel Optane, when having Optane inside vSAN as a cache layer, you have actually a comparable performance with using Optane also as an extended memory inside a physical server. Okay, however, the the gain that you can have from the vSAN cluster here is actually the high availability, because it's a virtual environment, so it has higher availability compared to the bare metal one, and the simple and flexibility in the resources management, because you are managing a virtual machine, not a physical machine, so you have more flexibility. However, from performance point of view, you have comparable performance. Yeah, so the conclusion here is using Intel Pearly, Skylake, and Intel Optane as a cache layer can save up to 25% of your physical server needs. We do not speak here only about the physical server cost, if you can also include the operation cost and the power consumption cost of these servers. So it's much more money to save when you use Optane inside to shrink the amount of servers required with 25%. Thank you.